Hello everyone. Can anyone please respond? Am I audible to all of you?
Okay. Yes, sir.
Yes?
Yes.
Okay, fine. So let us start. Why so less students today? So today we will start with SDOF and MDOF systems. That means what? Single degree of freedom and multi-degree of freedom systems. Now, the dynamic degrees of freedom are a set of independent displacements or rotations that completely define the displaced position of the mass with respect to its initial position. That means what? Suppose, can you see the slides? Can you see the slides?
Yes, sir.
Okay. So, if you can see here in the slide, this that U thing is a lump mass model. Okay. So this is what? This is a lump mass model. Okay. So now here what happens? This is a mass. This is a mass. Now this is the base surface where it is fixed. Now if this surface is vibrated, then what happens? This surface, this one is displaced by what? This U. Okay. So if this one is displaced by U, then what happens? Some amount of vibration is occurring. So that is a type of system. And another one is what? Here this one, in the second one. Second one, what is this one? This is a multi-story building. So it is having multiple degree of freedom system. Now every part of this building is having some displacements. Now look, if you can see this one, here this one is U1, this one is U3, this one is U2, this one is U1, this one is U4. Okay, sorry. So this way, what happens? It is vibrating in a different manner. This is what? Multi-degree. Now this one is the formula. Now look, the equation of single degree of motion of a system system is subject to an external force, and this is the following equation. Okay. So now if this is the equation, then mu double dot t, that means what? This is double differentiation. Then cu on t, that means what? It is differentiated on the basis of t. Then ku is equal to what? Pt. The term mu double dot t represents the inertia force due to acceleration u double dot t of the mass m. Now this is known as the inertia force. Now cu dot t, it represents the what? Damping force, which is equal to the product of damping coefficient and velocity. Now velocity and damping coefficient is cu dot. And ku is what? It represents the reactions that is produced by the system with stiffness k due to the displacement. That means what? There is certain amount of displacement, right? So this ku represents that one. Now this figure shows a single degree of freedom system with mass m, damping coefficient c, and stiffness k. This is subjected to external force what? Dt. The multiple degrees of freedom of system is the one which requires two or more coordinates to describe its motion. Now, in single degree of freedom system, only one coordinate is sufficient to describe the motion of the system. Whereas in multiple degree of freedom system, what happens? It requires what? Two or more degrees. Now, these coordinates are called generalized coordinates, and they are independent of each other and are equal to the number of degrees of freedom of the system. So this is basically the last unit of this semester. So after this we'll do all the revisions and all. Okay. In multiple degree of freedom systems, a natural state implies a certain configuration of shape that is taken by the system during the motion. So to clear all this SDOF and MDOF, let us watch some videos.
Dynamics again.
Can you see the video? Can you see the video, students? Can you see the video? Hello, can you see the video?
All right.
Someone please respond. Can you see the video?
Yes, sir.
What's up, everyone? Welcome back to Structure Free Learning, and in this iteration of a single degree of freedom systems. And hopefully by the end of this video, you will be able to describe a little bit what free vibration is, and in fact, and then formulate and solve an ordinary differential equation for a single degree of freedom system. And we also hope that you'll be able to describe the dynamic properties and look at some of the solution characteristics associated with that single degree of freedom system and the ordinary differential equation that comes out of that. Or hopefully, if you're watching this, you already are kind of familiar with what a single degree of freedom system is. So the first thing that we want to ask, what is free vibration? So a typical single degree of freedom system might look something like this. So I've got this mass and spring system. I'll call this with some stiffness K. And I won't include anything that looks like damping in it yet. So here's my typical or a typical single degree of freedom system. And free vibration would be if I were to pull on this mass, so I extend it a little bit, so I take it, I pull on it, I move it from here to over here, I give it some initial displacement, call this U sub 0, why not, right? I give it some initial displacement, and then I let it go and watch it move back and forth, back and forth. And in real life, that thing will eventually come to a stop because there's friction on the wheels, and then there's an inherent damping in the system that makes it slow down and stop. Another example of free vibration would be if you've got kids, like I take my kids to the park, and here they'll always want me to give them a push on the swing. So here, if this is my swing system, I'll put them on the swing and I'll give them an initial displacement. I'll pull it and then I'll let it go. And there's no machine or anything, and this thing is just going to oscillate back and forth, back and forth. And if I never push it again, or if I never introduce another force to it, it's going to just vibrate freely or oscillate freely, move back and forth until it comes to rest back where it started from, which was probably like right here. And all I'm describing right here is a pendulum. In this single degree of freedom system where we give it an initial velocity, so for instance, if I give them an initial push also and a displacement, that would be like an initial displacement and velocity. And then I let them oscillate freely until they come to rest. And they would come to rest because of that inherent damping. But free vibration just means I'm not putting any more forces on the system as it vibrates. And if there were no damping at all, this thing would just go on and on and on forever. Anyway, that's free vibration. Okay, so something with initial displacement and velocity, and then you just let it go. And then it moves back and forth until it comes to rest because of damping. And if there were no damping, it would keep on going and going and going. Now, knowing what free vibration is great, but as engineers, what we really want to do is know if we give it this much initial displacement or this much initial velocity, where will the particle or the mass be at any instant of time? And what does that motion look like moving back and forth so that we can do a bunch of other stuff so we know what the maximum displacement is or how fast it's going. We can even figure out the rate at which it's slowing down or see how damping affects the free vibration or the motion of the system. And then figure out ways to increase damping or control where it is when as a specific time, right? That's what we want to do as engineers. So let's start by looking at undamped free vibration. After reading the definition, they have an example of a child on a swing, but hey, I really thought of that on my own because, I push my kids on a swing for real. and also, after reading it, I also thought of a guitar string. If you pluck a string on a violin or a guitar and just let it go, that would be free vibration too. What's up? Now, the equation of motion is always an important thing. And the equation of motion for a single degree of freedom system, and let's say this point right here represents the at-rest state. So this is my origin or my equilibrium point. And we'll define motion going towards the right as positive. So I'll call this the motion of the mass as x. And this x or this position is a function of time here. And if I, do an equilibrium equation, or if I make a cut, draw a free body diagram, and do some of the forces in the horizontal, I can come up with an equation of motion which will look like this. And x double dot indicates the second time derivative. So really this is an acceleration, which would be d squared x over dt squared. And all the x's or the positions are a function of time. The m is the mass, k is the stiffness or the spring constant. And if you want to put something in free vibration, you have to give it an initial disturbance, right? You got to introduce something or some initial conditions. So those can come in the form of velocity or acceleration. So you could say that for initial displacement at time t equals 0, I could say that, I'm going to give this thing a pull. So I'm going to move at x of 0. I'm going to move it a distance, call it x naught. At time t equals 0, I give it an initial velocity. So I could say x dot at 0. I'm going to give it a push. And this will be, I'll call this x dot of 0. Boom. So this is like the pull, and this is the push. What I have here is an ordinary differential equation with some initial conditions, which means I can solve this using my math, my calculus, and get my position as a function of time for this whole thing based on these initial conditions. Hey, given all this, I can find the position as a function of time. I can have a solution for this right here based on this, the differential equation, and my initial conditions. That's really powerful stuff. And really, in the kinematics idea, what we want is to be able to describe the position, velocity, and acceleration at any instant of time for the particle or the system. Now, there's some interesting characteristics associated with this differential equation. So if I rewrite this and I divide this whole thing through by m, and in what they would call standard form, I would have x double dot plus k over m times x is equal to 0. And this k over m here is kind of a root of the equation. And this thing also has some really important properties. There's this thing called the natural or circular frequency, which we're going to use the Greek letter omega or lowercase omega. Omega sub n is defined as the circular or natural frequency of the system. And here, omega n squared is equal to k over m. So the natural frequency is equal to the square root of k over m. And the units of this natural frequency, these units are radians per second. Some people like to express this natural frequency in other units as well, like revolutions per second or revolutions per minute, like RPMs on a car, or cycles per second. And one cycle is the same as one revolution. One cycle is equal to 2 pi radians. If I wanted to express this natural frequency in terms of cycles per second, the symbol I would use would be F. This like cursive looking F, just a conversion. If I want to express it in cycles per second, it would be omega n divided by 2 pi. And this would be, typically the units of this is cycles per second or revolutions per second. In your car, it's revolutions per minute, so you got to convert the seconds into minutes, and that's a simple conversion. And then even what's more, I'll go towards the left here. What's more is there's another measure that people like to relate to the natural frequency, and it's called the period, which is the inverse of the frequency. The period is like another way to say how long does it take to complete one cycle. And this natural period is equal to the inverse of the frequency, or 2 pi over the natural frequency. In a second. Or if you're talking about natural period, it'll tell us how long. Frequency is a vibration property of the system. It tells us how many cycles the system will complete in a second. Or if you're talking about natural period, it'll tell us how long it takes to complete one cycle. Now what we want to do is solve this ordinary differential equation here and see if we can find the position of the particle or the system at every instant of time. I just have to recall my calculus, come up with a solution for this second order linear ordinary differential equation, which is homogeneous. As a side note, you may recall from your class in ordinary differential equations, this general or second order ordinary differential equation, which is homogeneous, in order to find a solution for y, which, it could be a function of x. In our case, it's a function of time. It really depended on these constants, a, b, and c, and in particular, as it relates to the quadratic formula. And I won't do that for us here. It depended on what this b squared minus 4ac. And if it was greater than 0, you had 2 real roots. If it was equal to 0, then you only had a single root. If you had b squared minus 4ac less than 0, then you had a complex solution. And that's the case that we have here. And for our ordinary differential equation, in this case, a would be equal to 1, b would be equal to 0, and c would be this k over m business. Since this b is 0, then I'm going to have negative 4ac, and that's going to be less than 0. And that means my solution x of t for this ordinary differential equation will have the form, and you can look this up, it's in almost any calculus textbook, and in this case alpha is equal to negative b over 2a, which really is just 0, so this term is going to go to 1, and this beta is equal to the square root of negative b squared minus 4ac over 2a. And if you plug and chug into this beta will come out to square root of k over m, which is just the natural frequency. So our solution to this differential equation, or our position as a function of time for this mass right now, is c1 cosine omega n times t plus c2 sine omega n times t. And then you can solve for these constants using the initial conditions. And if you remember, our initial conditions were that initial position or initial displacement that we provide, we call that x0, and our initial velocity was equal to, we said x dot 0. Here, I could say, oh, in order to solve for these constants, c1 and c2, I could say when x of 0 is equal to c1 cosine of 0, which is c1, and then c2 plus c2 sine of 0, which is just 0, is equal to x0. So we have one solution for constant 1, c1, and then if I take the derivative, if I take the time derivative of this equation right here, x dot of t, which is going to be c1 omega n negative sine omega nt plus c2 omega n cosine omega nt. And again, if I solve for x dot or the velocity at 0, then I would get this whole term here is 0, and I would end up with c2 omega n cosine of 0 is 1 is equal to x dot of 0, or the initial velocity. And this would tell me that c2 is equal to the initial velocity divided by omega n. And my solution, my final solution for position as a function of time for a single degree of freedom system would tell me that here x0 cosine omega nt plus sine omega nt. And here, if you were to plot this in terms of position as a function of time, it would look something like this. All right, that's as good as this graph is going to get for me. But this is the way the graph is going to look like. This initial distance right here, this value, this x0, is this initial displacement that I apply to the structure or to the system before I let go. And then the slope here, this slope at this point, the slope at that point right here, that slope represents the velocity. So that would be this x dot 0, that initial velocity that we provide. This right here would be the particle moving to the right, its furthest point in the right, coming back, passing the equilibrium point, and then down here would be the furthest to the left. So at this point right here, if I could draw this, it's just moving back and forth so that at this point right here, the structure, or my little mass and spring system, would be fully extended to be the furthest distance possible from its equilibrium point. So this, if this right here were the equilibrium point, this is this maximum distance traveled, or the amplitude of the vibration. So this distance from here to here represents the amplitude of vibration. We could just call this value c. Down here, my spring would be as compressed as possible, and at this point right here, my mass spring system might look really scrunched up spring. Boom, here's my mass and spring. And this distance might have been this is the equilibrium point, or when x equals 0, and now it is fully compressed. This is a distance c. That is the amplitude of vibration. The time it takes to complete one cycle is a period. So from here, if I go from here to here, this would be one complete cycle. Went from one side all the way to the other and then back. So that would be one cycle. This time, or this duration, we call the period, which is equal to 2 pi over omega n. And that, in a nutshell, is free vibration of a single degree of freedom system. Because there's no damping, the system reaches the maximum amplitude every single time. And if there were damping, these peaks would be decreasing over time. All right, hopefully that was helpful. Let me know if you have any questions. Take it easy. Structure free.
So this is an example of SDOF system. Look how the vibration is taking place. If you can see, the bodies are not vibrating, but the initial has been given displacement. Look, now it is vibrating. Now this is based upon the distance. One is vibrating, one is not. So in this way, it will be different. Now look, the vibrations are increased. So this one is vibrating at the last. So this is how the vibration is established. And if this vibration of this base plate and this one matches, then it shakes very highly. So this is the resonance state that is achieved in the number one. Okay. This is for the multi-degree of freedom system. If you can see, the vibration is occurring at different hertz. So here it is resonance is achieved. Look, it is shaking so highly, no? So this is what is resonance. Now again, at certain time it will come down. Again after some time it will again occur. Look, the vibration patterns are different. Initially, it was shaking in a different way. Now it is vibrating in a different way.
Sir,
Hmm.
it's high,
Hmm.
and the bigger one
This is because of the
vibrates
different
when
resonances.
frequency.
Because of their different resonances and because of that distance. Okay, the height. Okay.
Uh, uh, it should be uh, uh, vibrate high when there should be frequency
These
when
are
we
for
increase the frequency, sir.
different modes. Okay. These are for the different modes. It is vibrating in that manner. That is what I am showing. We think it in different order, but it happens in a different way. Okay. Understood now? जो सोचता है वो नहीं भी हो
Yes, sir. Yes,
सकता
sir.
ना, तो वो डिफरेंटली हो सकता है ना. So
Uh-huh.
that is where the different lies. Okay,
Uh-huh.
briefly.
Okay. So, sir,
बोलो.
so in practically, if we increase, suppose I am driving a car. So if I increase the speed of the car at some bed road, जहाँ पे मतलब there will be vibration will be more.
देखो, वो वाइब्रेशन का
So
डिफरेंस तुमको मेरी जगह कब पता है? जब स्पीड ब्रेकर क्रॉस करता है ना, मल्टीपल स्पीड ब्रेकर, व्हेन यू आर ड्राइविंग योर कार,
yes,
यू
sir.
सी
Yes.
एट वेरी लो स्पीड ऑल्सो द कार वाइब्रेट्स वेरी हाईली. ठीक है, लेकिन अगर एक पर्टिकुलर स्पीड है जहाँ पे इतना ये फील नहीं होता है तुम लोग का वाइब्रेशन का. समझ लिया? वही है डिफरेंस.
Okay. Okay.